Hey everyone, and welcome back. Today, we are diving into a concept that is, no exaggeration, at the very heart of pretty much every digital device you own, sequential circuits. We're going to break down what they are and why they are so incredibly important. So let's jump right in. So what makes these circuits so special? Well, it really is all about their connection to the past. See, their defining feature is that they can remember what happened before, and that simple idea, it's a complete game changer in the world of electronics. Okay, here's the core idea. A sequential circuit's output depends on the present input and its past inputs. And that last part, that's the key right there. Unlike simpler circuits, what happened in the previous step directly influences what's going to happen next. Look, if you remember just one single thing from this, make it this. A sequential circuit is a circuit with memory. It can store information. It can remember the state it was in. This is the foundational concept that everything else we're about to talk about is built on. Let's make this crystal clear by putting it side by side with another type of circuit. So on one hand, you have a combinational circuit. Think of it like a simple calculator. It only cares about the numbers you're punching in right now. But a sequential circuit, it looks at the current input plus its previous state. That plus previous state bit, that's what gives it its memory and all of its power. So how does it actually remember stuff? I mean, what's going on inside the box? Well, let's break it down into the three essential ingredients that make this memory possible. Okay, so at the very heart of it all, you've got flip-flops or latches. These are just tiny little elements that can store a single bit of data, a 0 or a 1. Then, to keep everything in sync, there's usually a clock signal. You can think of it like a conductor's baton telling the circuit exactly when to update. And finally, you have the combinational logic. This is kind of like the brains of the operation, processing inputs and deciding what the next state should be. So here's how it all comes together. First, an input is applied. The logic gates chew on it and process it. And then, and this is the crucial part, a flip-flop stores the result as the circuit's new state. So the next time an input comes along, the output is going to depend on both that new input and this state that it's been holding on to. What this does is it creates this really powerful feedback loop. The output from that memory element literally feeds back into the logic part of the circuit. This loop is the actual physical mechanism that allows the circuit to remember what happened to the past. It's pretty cool. Now, sequential circuits come in two main flavors. The most common are synchronous circuits. They use that clock signal to make sure everything happens in perfect time, like a well-rehearsed orchestra. Asynchronous circuits, on the other hand, don't use a clock, so they react instantly to any changes. They can be faster, for sure, but they are way trickier to design correctly. All right, enough theory. Let's talk about how this all translates into the devices we use every single day. I mean, where do these circuits actually show up in the real world? Let's look at probably the most fundamental building block of all, the D flip-flop. It's the perfect, simple example of a one-bit memory element. So here's how this little guy works. You've got an input D for data and an output Q. When that clock signal ticks, the output Q simply becomes whatever the input D was at that exact moment. And then it just holds on to that value. It remembers it until the next clock signal comes along. It's so simple, but it's incredibly powerful. And when you start stringing these simple memory elements together, you get, well, pretty much everything in our digital world. The digital clock on your wall, it uses them to count seconds. Your computer's registers, they use them to hold data for calculations. They are the absolute foundation of computer memory, like RAM. In fact, the CPU in the very device you're watching this on is built on millions, if not billions, of these sequential circuits. All right, let's wrap this up and go over the key points you'll want to remember. So here are the 4 big takeaways. First, their output always depends on a previous state. That's the whole memory thing. Second, most systems are synchronous, meaning they use a clock for precise control. Third, because they rely so much on timing, they need a really careful design to avoid errors. And finally, they're absolutely foundational to all modern electronics, from your phone to massive data centers. If you boil it all down to one simple equation, this is it. A sequential circuit is just the combination of logic and memory. That's it. That is the magic formula that powers our entire digital world. And honestly, if you've been able to wrap your head around this core idea of logic plus memory, you have taken a huge step forward. This is one of those cornerstone concepts that really unlocks a deeper understanding of how all of our digital tech actually works. So, what should we tackle next?
Should we do a deep dive into all the different types of flip-flops? Or maybe take a look at how they're used to build counters? Let me know your choice down in the comments. Thanks for watching, and I will see you in the next explainer.